Hello, everyone. My name is Rachel Del Porto. I work with Dr. Christina Poindexter at Sacramento State in the Department of Civil Engineering, and I'm going to be talking with you about the use of rhodomine WT for the characterization of hydraulic residence times in wetlands. So a little bit of an overview. I'm going to take you to the site we're looking at, some of the objectives we have. I'm going to go into some previous tracer releases and what came of them, and then some literature reviews of different hydraulic parameters. Then I'm going to go into different experiments, both batch and mesocosm, that we did this semester. So to start off, many of you may know about the Sacramento-San Joaquin Bay Delta. You may be familiar with it. This is a set of islands between Sassoon Bay and Stockton. And these islands are a little bit different than the normal islands everyone is used to. They're not actually islands because they're above the water surrounding it. They're actually only islands because they're kept dry by levees. So when you're standing in some of these islands, you can actually look up and see boats passing by in the water above you. So what happened here was in the 1800s, these islands all used to be wetlands. And farmers quickly found that the peat soil located in wetlands is fantastic for farming. They produce great crops and great yields. So they began to drain these wetlands to then use them for farmland. However, the issue that occurs when this happens is that once that very highly organic peat soil actually touches the atmosphere, it oxidizes very quickly and breaks down. So what happens is your land surface may have started here, but once you start to drain the wetlands, it begins to subside and actually go down. And so this is how you get this kind of bathtub effect where your islands aren't islands like this, they actually dip down like so. And the issue there is as subsidence gets more and more prominent and as water levels rise, and as levee infrastructure begins to age, the pressure, the hydrostatic pressure that's located on these levees makes them highly susceptible to failure, and these islands could then flood. You all may remember not too long ago, the Lower Jones Tract and the Upper Jones Tract islands down in the bottom right-hand corner of the screen actually failed. A levee failed there and those islands flooded. It's a lot of money to be able to pump the water back out of those islands. Farmland is lost. Cattle are on some of these islands, and some people live on these islands. So it's a huge catastrophe and a huge crisis when one of these levees fails and one of these islands actually floods. And also, many of these islands, the levee system in them are in a series kind of effect, which means one failure could cause more and more failures. So we want to protect these levee systems as much as possible, which is why people are beginning to reinstate some of these wetlands to try and promote accretion, which is the opposite of subsidence. It's actually the increasing of the land surface level. And it is thought that if you reintroduce these wetlands, then the peat can grow over time and that land surface can actually increase. So we're specifically looking at Twitchell Island here. It's circled in red. Here's an up close of it, and we're specifically looking at West Pond, this gold here in the middle. Now, West Pond is a wetland that the Department of Water Resources reinstated, and they're looking at its ability to accrete land. Also, its ability to sequester carbon dioxide. It is thought that wetlands may be able to sequester a significant amount of carbon dioxide. So all of what we're looking at is happening on this island. And we're specifically trying to figure out what kind of hydraulic parameters are best for wetland accretion. So meaning what depth of water is best, what flow of water is best to cause this land to accrete at the quickest rate. So to do that, we need a tracer. So rhodomine WT is the tracer we're using. It's this tracer chemical you see here on the right. It's a bright pink fluorescent dye, and it's used for aquatic systems. It's non-toxic to the environment and aquatic life, which is important, and it's non-reactive. So what that means is we have fluorometers that measure the fluorescence of rhodomine WT when you stick them in water. And since it's non-reactive, when you see a reading on that fluorometer, you know that it's rhodomine WT, and you don't have to worry about it being something else or rhodomine WT reacting with something else. Rhodomine should also be conservative. However, what we're finding is that in these West Pond tracers, it's not actually being conservative. So what conservative means is when you put it into the water at the inlet, you should be able to measure it in the water at the outlet. It shouldn't be absorbing onto the soil. It should all stay in the water phase. However, we're seeing that that's not quite the case with rhodomine WT. So our overall objectives, we're trying to determine the cause of and the extent of this rhodomine trace resorption in the Twitchell Island wetland, and we're trying to determine how hydraulics affect the accretion rates in Twitchell Island. Then we want to go on to analyze accretion rates and the use of rhodomine WT in different wetland water types. So looking at some previous tracer releases, down the right you can see a picture of what it actually looks like. That's the bright pink rhodomine WT. 21% was recovered in a Lin et al. Study, which was a wetland that was not the West Pond wetland. And 21% isn't a very high recovery rate, but it's much higher than the 4 and less than 1% recoveries that were seen in 2 different tracer releases in 2 different years at the West Pond wetland. So we're seeing that not very much is actually being recovered at the end, which suggests that it is not conservative and that sorption is happening to the peat soil. So this is the breakthrough curve of one of the releases at the West Pond. And what this peak shape you see here shows, it actually has kind of 2 peaks in one. And what that suggests is that there's either parallel paths, so maybe one path goes around a tree and another is a straight shot. So one arrives at the outlet a little bit quicker than the other. Also, rhodamine WT does have 2 isomers, so it's possible that one is arriving at a different time than the other. And as you saw in the past slide, the concentration at outlet was only 4% of the concentration at the inlet. The estimated hydraulic residence time, if it's modeled as a plug flow reactor, was calculated to be 6.4 days, but was less than 1 day at actual experimental, which suggests that it's moving much, much quicker than it is expected to and calculated to. It's also found that the Peclet number is greater than 1, which suggests that advection, or the forward motion with the flow of water, is the primary mode of transport rather than diffusion out from the primary flow of water. So here are some hydraulic parameters. These are all numbers that were calculated using the September 2018 tracer release. So what you see here is different literatures, different authors who have created different calculations for different hydraulic parameters. And so not every single literature has every single value, but you can see that there are some duplicates and some triplicates. And you can see that there are different numbers between 0.76 and 0.39, for example, between Holland and Pearson. So what we're trying to figure out is we're trying to do more and more of these studies to figure out which of these literature calculations best suits the West Pond, so that in future, when we're trying to measure accretion rates alongside hydraulic parameters, we know which hydraulic parameter calculations are aptly fit to this particular wetland. And here you can see our batch experiments. So these are part of the experiments that we actually conducted this semester. And what we did was we took actual peat soil from the West Pond and we placed it in different beakers. We placed different known masses in beakers with known concentrations of rhodamine WT. We left it there for a week, let it stir continuously, and then we measured the concentration of rhodamine in the water at the end. So what we were trying to see is if you had more peat soil, did more rhodamine sorb to that peat soil, and consequently you see less in the water at the end of the experiment, which turned out to be true. The more soil that we had, the more adsorption we saw, which goes to further conclude that rhodamine WT actually does sorb to this peat soil. So the more soil we had, the more rhodamine was taken out of the water. We want to look at mesocosms as a wetland model, so that was our next step in our experimentation. So mesocosms, they're like this picture you can see in the bottom here. They're metal horse troughs, and they use the same soil and the same plants that are in the West Pond wetland, just on a smaller scale. So we can measure hydraulic parameters in these mesocosms, as well as accretion weights in these mesocosms, and then be able to model it up and scale it up to what should be happening on a wetland scale. So we did one experiment using mesocosm desorption. So as you can see in this picture here, here's our mesocosm. And it did experience a tracer release, so there was some rhodamine left over in the soil in this mesocosm. So we tried to desorb that rhodamine to see if it was possible, and it was. So at first we used pumps for those first 2 experiments, which had a really high flow rate. And we found at the beginning of the experiment there was much more rhodamine in the water than at the end of the experiment when water had been flushed through, which makes sense. But after the water was able to sit in the soil for a week, you could see in the second desorption that it went back up. The ppm, the parts per million value, actually went back up. So more rhodamine was being drawn out of the soil and into the water. And you can see in this third siphon experiment, a siphon has a much slower flow rate. So the water was in contact with the soil for much longer. So the rhodamine concentration didn't dip off as quickly. But overall, we can see that there was rhodamine being desorbed from the soil. So our next steps, we're going to go ahead and compare rhodamine and fluoride as wetland tracers to see which is better, or if they're best used in tandem. And then we're going to go ahead and use those mesocosms to go ahead and model hydraulic parameter effects on accretion rates. So we'd like to acknowledge Katie and Danielle for all of their contributions to the tracer releases and data. I'd like to thank Dr. Christina Poindexter for allowing me to work with her, and we'd like to thank the judges for allowing us students to still participate in this research competition despite all that is going on. Thank you, and I look forward to your questions.